We've now seen how a call chain gets translated into stack frames, how each call puts a new stack frame on the stack, each return takes one off. So now let's go into a little bit more detail on what's inside of those stack frames. So we're going to look at the Linux stack frame, what's used in the IA32 conventions. Again, the stack frame, in this diagram I'm showing the caller stack frame, which includes a bunch of arguments that it's set up for the callee and some other space that it might have used for its own temporary variables. And then when it makes the call, it also stores the return address that it wants the system to return to when the callee procedure is finished. Okay. So what the caller has done is built up a bit of an area here where it's put in the arguments to the callee function, and then a little bit more space for that return address. Okay. What happens next in the callee's frame is that we have the old base pointer of the caller's stack saved, of the caller stack frame saved. We're also going to save some other registers that we might want to be able to reuse, so we'll have to restore these before we return. And then, of course, some local variables as well that we might want to use in the callee procedure. And we'll get ready building up arguments for any other functions that we want to call from this procedure. Okay. And, of course, as we do this, the stack pointer will continue to move as we add more and more things to this stack frame. Okay, so that's the basic idea. Let's see this in the context of an example. Here we're going to go back to that swap function, swap procedure that we had. Do it a little bit differently this time. Here we have a function called call swap, which doesn't do very much. All it does is it calls another procedure called swap, with two arguments, two addresses, you'll notice, right? Two addresses there for the two variables whose values we want to swap. So the address of zip1, the address of zip2. All right, here's the definition of the swap procedure. You notice that it has its two arguments described at the top. They're both pointers, and they're both pointers to type int. So these match up because, of course, our two zip variables were ints to begin with. All right, what we do then is have two temporary variables, t0 and t1. We load them up with the values stored at those pointers. Remember, we're dereferencing the pointer, going to get the value at that address. That's going to be the value 15213 and 98195. Then we take those temporary values and put them in the opposite location. Again, dereferencing the pointers. Okay, that's our function call swap and swap, our two procedures. All right. Call swap is pretty easy to see in assembly code. What it's going to be doing at least the parts we care about are going to be doing something pretty straightforward. They're going to be putting the two arguments onto the stack using push instructions. Okay? These will push the two addresses of the two variables onto the stack. And then it's going to execute the call swap to get the callee procedure started. Well, before we get to that, let's take a look at the stack then. At the end of this, we'll have had some previous stack, of course, and then we've added two values doing the push instructions, those two addresses for our two arguments, and then, of course, we've added the return address of the call, which is where we want to return when we execute the return statement in the callee procedure, in this case, swap. Okay? So that's now the contents of the stack. All right, so now let's go look at what swap looks like in assembly code. And here we have that setup code you've seen before in other examples. some finishing up code that we've seen in other examples, and we've ignored this for the most part until now. Now we'll talk about it in some detail. And here's, of course, the body of swap that does the actual flipping of those two values. All right. So what we're going to do is look at this in a lot of detail in the next few slides. Let's start with that stack that as it was when we started executing the swap procedure. So here's the first few instructions of swap, that setup code, right? What happens after these instructions execute? The first three instructions. All right. So the stack starts off with having a new value added to it. You'll notice here we have a push of the register EBP onto the stack. So what did EBP point to? Well, it was pointing to the base of the previous stack frame, the one for call swap, and we've just saved that pointer onto the stack, okay? And of course the push instruction also changed the value of ESP to now point to this new top of the stack. Okay. The next instruction is a move instruction that takes the value of ESP and moves it to EBP. This is setting up the new base pointer for the new stack frame for the swap procedure. Okay. So right now both of those pointers are pointing to the same location, the top of the stack. The very next instruction pushes the value of VBX. This is maybe a register that we're going to use inside a swap. So we're going to push that value onto the stack so we can restore EBX before we return. Okay, so we've just pushed that onto the stack. The stack has grown some more. You notice that ESP has been adjusted yet again. So now ESP and EBP are not the same any longer. We're starting to grow that frame down. In this case, by saving away a register we need to restore later. All right, next step is to start looking at the instructions that look at the arguments to the function. Those were these two, the next two instructions of swap. And what is going on here? You'll notice that we're taking the current value of our frame pointer, the base pointer to our frame, and adding 12 to it. Okay, so we're taking that address, remember the parentheses in this case mean use the address stored there, add 12, go get that value and put it into ECX. Okay, so what does that mean? Well, if we go to EBP, it's pointing to this location here. When we add 12 to it, we're now pointing to this location, which is where we've stored one of our arguments. Right? Because we're starting our frame right immediately after the previous frame, we know that if we just do a little bit of an offset, we can get to the value of those arguments. That's that calling convention. The fact that we've put those arguments in a certain order right there at the top end of that previous stack frame. Okay, so this lets us get to YP, that first pointer argument, and then this statement adds 8 to that same pointer to go get the other argument, XP. All right, so this is why we see these frequently at the top of a procedure. The instructions to get the arguments. We've now have the arguments stored in ECX and EDX. Once we have the arguments, of course, we'll perform the operations of the swap function, but we've seen those before already. So let's skip ahead and talk about the finish portion of swap, those instructions at the end that clean things up. Here we see a move instruction that takes the base pointer, subtracts 4, so we're actually going to look at this location, 4 down from the current value of our base pointer, and go take that value and put it in EBX. In fact, that was the old value of EBX, so we're going to restore the value of EBX to what it was previously. Okay, so we've saved and restored the register EBX and put that back exactly where it was when we came into the function. The next instruction again copies the value of the base pointer into ESP, and you notice that's the adjusting the stack so that we don't think about the value, the old value of EBX being at the top of the stack. Now you might ask, why didn't we use a pop instruction here and move the value at the top of the stack into EBX and automatically add 4 to the stack pointer to get that adjustment? Well, we could have done that. It would have been the equivalent thing. This is a bit of an optimization, because if we had to do that for several registers, we could use some faster move instructions to do a bunch of things at the same time rather than the pop instructions. But essentially, those two lines are equivalent to a pop instruction. And you'll notice that the very next instruction is another pop, this time to take the old value of EBP and put it into the base pointer register. So now we've back to the state where we were when we first entered the procedure swap, with the frame pointers, the base pointer pointing to the top of the frame for call swap, and ESP to the bottom. At this point, we can execute the return instruction and use that return address that was at the top of the stack, pop that off, and jump to that address, which is that one immediately after the call instruction inside of the call swap function. Okay. And of course, with the arguments are left on the stack, now it's up to call swap to remove those arguments if it needs to. Or it could choose to just leave them there and return itself, having its stack pointer adjusted to the previous frame for the function that called it. All right, so let's go back to look at all of the code for the swap instruction. Here are all the instructions for the procedure. And the code that called swap from call swap maybe consists of these few lines, as well as maybe other things that were in that other procedure. I'm not showing all of those here. You notice here's the call instruction. It had to provide the address of swap. Of course, the address actually stored in memory is a relative address, as we've seen before. So you'll notice that this is a negative value, and because it has leading FF there, so it's a negative value. So we're actually going to subtract a little from our current address of 409, probably enough to get us to 3A4, which is the start of the swap procedure. Okay, and we can get listings like this, of course, using GDB. Okay. The return value that was stored on the stack was this address ending in 840E. You notice a different instruction here called leave. Leave is just a shorthand for, in fact, the equivalent two instructions, move EBP to ESP and pop EBP. Because those are so common, we always use those in combination as the very last two instructions as we finish up a procedure and clean up. They've actually been given a special code in the x86 architecture using the keyword leave and a code of C9 for its opcode. The last observation to make is that although we saved and restored the register EBX, we didn't bother to do that for EAX, ECX, or EDX. We just didn't bother saving those at all. And why not? We use those registers as well in the code, turns out. Well, the reason we didn't save them is because our convention is that the caller needs to save those registers. We're going to talk more about this in the next section.